Hello, my name's Ben Klukaszewski, and this is Physics 2212. Today I'll be going over Lab 1, Charged Tapes. Alright, so there can be four main parts to this presentation in this lab. First up, the introduction will be the description of the lab and the fundamentals. Second of all, observations, data, and calculations, which will be a setup, results, and analysis of the data. Third of all, we'll have GlowScript, which will be the actual computerized code part of the lab. It will give us a visual representation of the data. And finally, we'll move on to final questions and a few final thoughts on the matter. So, introduction. The goal of this experiment is to use clear Scotch tape to observe, analyze, and estimate the transfer of charge. Now we're going to represent the charge of these pieces of Scotch tape as point charges. And the charge tape will be introduced to the opposite piece of charge tape to produce repulsion. Now the goal is to determine how much charge is present on a piece of charge tape. Now the principles we're going to use in this experiment are threefold. First of all, we have Coulomb's law, which will be used to calculate the electric force. Second of all, we'll have Newton's second law, and third of all, his third law. These will be used to determine gravitational force and interpret equal and opposite forces. Alright, we're going to go on to assumptions and results. What assumptions, approximations, or idealizations did you have to make to determine approximately the amount of charge on the floating tape? In this, we have to make the assumptions that A. Air resistance was ignored on moving objects, B. The tape was treated as a point charge, with the center of the tape acting as the point of charge, and C. It would assume that each U of tape has approximately the same amount of charge, evenly distributed across the tape. Alright, for the Sepa experiment, we have some base parameters and measurements. For instance, the length of our tape ended up being 0.2 meters. The mass of the piece of tape ended up being 0.0002 kilograms. When the two pieces of charged tape were introduced to each other and repulsion was observed, the repulsion ended up being about 2.8 centimeters. Now we can calculate the magnitude of gravitational force acting on the floating piece of tape, and it comes by using the formula F equals mg, and it comes out to about 0.00196 newtons. Now, since this piece of tape is floating, we automatically understand that the magnitude of the electric force acting on the floating tape is equal to the magnitude of the gravitational force, since it's remaining suspended in midair. As such, the magnitude is the same and is also 0.00196 newtons. Next up, we have calculations. In this particular one was calculating the magnitude of the charge on one piece of tape. In here, we are solving for Q, and we can use it using the we can find it using the equation mg equals k q squared divided by d squared. Again, this is made with the assumption that the two points were equal point charges. In this case, Q ends up being about 1.31 times 10 to the negative 8th coulombs. Next up, we'll have electrons present on the tape. In this case, the number of electrons on the tape can be found by dividing the charge of the tape by the charge of one electron. In it, we get about 8.17 times 10 to the 10th electrons. Tape area, it can be easily found by multiplying length by width. And the area of atom is easily found by squaring its length. The overall result of atoms on the tape is as follows, which is approximately 4 times 10 to the 17th atoms. Now we can calculate the electron to atom ratio. Now that we have the necessary measurements, we can simply divide the number of electrons by the number of atoms present on the tape, which yields approximately 2.04 times 10 to the 7th electrons to an atom ratio. Nearly last up, we have our GlowScript code and model. To the top right, you'll see the visual representation of the data. Tape A and B are shown as point charges in the model on the right. Tape A is shown as the red sphere, and tape B is shown as the blue sphere. The yellow arrow pointing downwards is the gravitational force acting on tape B, whereas the green arrow pointing upwards acts as the electric force acting on tape B. Below the model, important information like the charge of the tape, the overall force acting upon it, and the estimated number of electrons within the tape are present. To the left of that, you'll see the code that I used to produce this visual model. Finally up, we have the few remaining questions and final thoughts. So first up, if electrons had positive charge and protons had negative charge, would anything change about the observations or experiment? Simply put, no, nothing critical would change in the experiment. The interactions would remain the same, since like charges repel regardless of whether they're negative or positive. Secondly, why is it important to handle the charged tapes as little as possible, and what could happen when the charged tape comes into contact with your hands or other objects? This is because charge can be inadvertently transferred when contacting your hands or other objects, which would result in a loss of charge and ultimately an inaccurate experiment. Thank you.